Satoshi Matsuoka to come back to the Google Cloud Advanced Computing community for part 2 of the presentation that he started several weeks ago, and everybody eagerly wanted to hear more. So Satoshi, thank you for joining us again. Happy to have you back.
Thank you, Jay. And thank you for everyone for either coming back or maybe you're hearing this talk anew. And so really appreciate your time. And so I'd like to present my part 2. Just to go over a few of the things I talked about last time, and hopefully I can get my windows to behave. Oops, how do I? Okay.
Yeah, you're in the slide sorter mode right now.
Yes, I know. Okay. So I'm Satoshi. Just to make sure, I'm Satoshi Matsuoka. I'm the director of RIKEN R-CCS. It's the National Supercomputing Center of Japan. We do research, development, also deploy machines, machine like this, Fugaku, which is a 160,000 node machine we have currently right now. Now, so we talk a lot about AI for science, some of the app, the real AI for science being done on machines like these, and also other instruments and so forth. And we'll also talk about our new supercomputer we're planning, Fugaku Next. But I'd like to kind of backtrack a bit and first start with the rationalization of why we may want to really seek convergence of cloud and HPC and traditional HPC with AI. Yeah. So when you look at the current infrastructure, ABCI is one of the successor to one of the AI-based supercomputers that I built back in 2018. Now the 3.0 is the 2025 machine that my successors have built. So when you look at like ABCI, hardware, software, these AI supercomputer, and also the software, and compared to something like Amazon or Google, they are very largely the same. You have the same sort of CPUs, you have the same sort of GPUs, you have memory, you have an operating system. You may have a little bit of difference in how you may deploy resources. I'm sorry, a little Japanese, but it's a development environment. Okay, so so basically, supercomputer technologies have transcended into the cloud, and then of course we have this significant revolution of AI driven by these supercomputers in the cloud. So what did it really look like in a quantitative fashion? So this is the graph that shows the evolution, the growth, the performance growth of AI. The way I qualify the AI performance, of course, there are many ways to do it, but this is a very gross approximation saying how many AI-capable machines there are. AI-capable meaning those that support lower precision arithmetic and thus be able to run transformers, etc., at higher performance. So again, this is a gross simplification, but it just but it sort of gives you a good yardstick to determine what the growth rate had been. So in 2018, of the 500 systems on the so-called top 500 list, there were 71 of such systems that would qualify as sort of AI capable, modern AI capable. And in 2025, about half of the systems, 229 of 500 systems, do qualify. Now, the cumulative performance gain over this 7-year period. And 2018 started because that's when we had NVIDIA Volta that had the Tensor Core FP16 acceleration, matrix acceleration. So it's been about 92x in 7 years. And during that time, the HPC performance only grew by 11x. So we got about 8x performance gain compared to the standard performance gain in HPC. So of course, this was driven by significant advances in the hardware, acceleration hardware, AI, in terms of accelerating AI due to, of course, heavy demand of AI. We also look at the country share. And the orange line you see on the top is the United States. And you can see that by and large, it has kept about 50% of the share. The blue line is Europe. So you can see that Europe has certainly gained the share overall. China has decreased because China decided not to put machines on top of 500. So their downfall is somewhat synthetic. The yellow line in the middle is Japan. So we see that Japan has been hovering around somewhere around 8 to 10% during that time. Okay, so that's for the supercomputers. And if you look at the left chart, this is the top 500 FP64. So this is the real cumulative performance for the LIMPAC, FP64 LIMPAC. And if you compare this share and the overall trend for the past 7 years versus the trend of the AI, the share. Of course, the growth has been significant. The absolute growth has significant, but the share have been largely the same across countries. For example, Japan's share in June 2025, the same period, is 7.8%. So it's about the same. If I go back, it's about 8%, 8.6%. Top 500 share is 7.8, so about the same. But the growth of the AI performance for the top 500 machine has been about 1.9x, 98 which means that, again, it has grown 90x, and over the course of 10 years, it would have grown 6-7-fold. So, we are, so this says that we are witnessing where a lot of performance growth are being realized in our hardware. Of course, we know this in the supercomputing hardware. Of course, we know this, but but we're not glossing over the metrics here. We have a real bona fide number saying that the AI performance growth has outstripped standard supercomputing growth by a factor of 10. And that's why, and since we are focusing on supercomputer performance gains, plus AI performance gains, that's why the hyperscalers such as Google are, working with people like us in the supercomputing arena. That's why you have people like Jay, who's an HPC, who has been an HPC person, work for Google. So it's a natural convergence there. In fact, the growth has been even more significant. So those are just the top 500 machines. So we all know that there are a lot of reports with varying numbers, and of course these numbers are fairly dynamic. So I think every day we get more GPU installations in the hyperscalers and neoclouds. And US has been, of course, most prominent. And if you look at the trend of the overall AI compute share, so this is not just the top 500. These are like all the machines that are AI, that are serving the AI in a cloud. And you can see that the US has been dominating in this as well. In fact, you can see this like swapping the lead between China and the US. But if you look at the bottom list, then you'll see this also in the animation, that the US has regained the lead. In fact, now it is really dominant. It has about over 60% of the global resource in AI. Of course, China is also trying its best to sustain its share, and they have incubated talents across the stack. So that's why you have like DeepSeek and Kimi and Transcend, those companies. Europe has been investing in various supercomputing centers because their public clouds, like Japan, are not as strong. So now that AI factories and AI gigafactories, although shares has shrunk, they are out to try to actually, at least try to match the status of the US. Japan is kind of trailing behind, and that's very concerning, but that's a very different subject matter. So so right now, because you see here, US has 67% now, and EU has 4%, and Japan has only 1%. So There's significant US dominance here. And that's why, we are out to build the technology, and that's Fugaku Next. And that's what I covered last time. Okay. Now, so in building these advanced supercomputers, because of this obvious growth of supercomputer performance, right? We want to build supercomputers that are, of course, very capable in AI, and we get those naturally, as you have seen. And this is very much evidence in the graph. We all know this is happening. But again, making those numbers concrete, and also this determining a trend will actually give you these the actual the ability to exactly extrapolate the growth in performance. On the other hand, and a lot of people say that because of this emphasis in AI, traditional supercomputing is being sacrificed. That we are no longer because all the computational resources are so much being focused on AI that there's going to be a divergence of HPC and AI, and that for an HPC community, that may not be favorable because as much as AI is important for obvious reasons, but also traditional first principle simulations are also important. In fact, we want both to proliferate. So what we are trying to do with Fugaku Next, our next machine, is to work with our vendor partners and also work on the algorithms, work on the software, doing full analysis of the various algorithms to see if there can be convergence. In fact, we are very confident that we can achieve convergence in such a way that we can significantly exploit this hardware trend to accelerate the HPC software well beyond what would have been capable. So by having AI accelerate, we can go even beyond the traditional performance growth curve. We also need to incorporate new modes of operation. If I have time, I'll cover that. But the main talk will mostly consist of what we think, where we think HPC will benefit by this acceleration of AI. So there'll be convergence, not divergence. Okay. So first we cover dense linear algebra. So this is, for example, molecular dynamics, first principles, materials, like material science code, like our orbital, ab initio science codes, some codes like acoustics, etc., where dense linear algebra is necessary. Now, when you look at the current trend, where we have the so-called matrix engines or tensor cores, we have these in GPUs, we have these in TPUs as well. The trend has been that we have low precision matrix multiply, and the so-called and this is typically implemented as and so some sort of what are typically called historic arrays, and the tendency is for low precision matrix historic arrays to get bigger and bigger. I think the latest TPU is like 256 square, 128 or 256 square. So that's getting bigger. Now, some of the GPUs have had high precision matrix engines, like 64-bit precision matrix engines. For example, NVIDIA's Hopper has 2x2 64-bit matrix array, so that doubles the performance. But in reality, this high precision matrix multiplier really doesn't make sense in terms of, well, it's disadvantageous in terms of hardware circuitry. Because in low precision matrix multiply, it makes a lot of sense to have the matrix unit. Because these historic arrays work in a way such that, see this, you have the data coming in from the top or the left in this figure. Let me actually give you a pointer here. Yeah, so data will come in from the top and the side, and you'll do matrix multiply, and the results come out on this side. Now, so the volume, the compute is actually done in these units, and the data movement are done between these two units. So if you know HPC, this constitutes with the small matrix engines, you may have like FP16, FP float, even FP8, FP4. The multiplier and adders in these circuits are trivial as you go to lower precision, but you still have to transfer the data. So there is a the degree to which the circuits shrink as you go to lower precision is higher, right? Because if you grow it, it's the opposite. You get the complexity of the circuits increase by at least a log n or even more. So this means that with low precision matrix multiply, the surface, that is the communication, mostly dominates. So you want to pack these multipliers together as much as possible, right, for optimization. So it makes a lot of sense to pack all these matrix multiplier and adders, mostly possible, many of them, so that you get minimal distance of communication between these two units. So that's why these make sense. Whereas high precision really doesn't make sense because the circuits here, the matrix units are really big. You know, there are 64 bits, for example. The Matrices has 53 bits. But you're only communicating 53 bits here. But here, internally, you know, it's more than order n. It's at least a log n, which higher complex, n squared higher complexity in some cases. So that means that you get lots of compute with very small communication. So it really doesn't make sense. You can might as well, you know, get the data out of here and store it in the register and then feed it here. So these would just be vector operations and really doesn't make much difference. So high precision matrix multiply by vector is sufficient for the most part. You know, it really doesn't matter in terms of performance or for energy consumption. So a lot of people get sad when some of the more modern GPUs, for example, NVIDIA, go from Hopper to Blackwell. NVIDIA decided not to deprecate the high precision matrix multiply. But, well, of course, the one argument is to reserve space, to not have this space here, but to utilize a space for small matrices, because that's what AI is. But that's not the only reason. The other reason is having high precision matrix multiply units, matrix multiply, this historic array of matrix multiply units really isn't beneficial in the first place. So that's why this stuff proliferates, whereas the right hand does not. And we really can't change it. It's physics, so we can't change that. So it's not just commercial benefit. It's the physics. So we have to kind of divide the applications into different classes for like deep learning, AI training, inference, etc. This low precision, of course, that's what it's for. But we have to adapt our algorithms to utilize these low precision units as much as possible to go beyond what would have been possible using the hardware high precision units. In fact, that's an opportunity because now we have algorithms that will allow the utilization of these so that it'll be better than facilitating these hardware units. So for moderate precision, we have higher mixed precision. And for matrix multiply based algorithms like material science, we have what's called an Ozaki scheme, which are my colleagues at RIKEN and other universities invented in Japan. And we can say that these algorithms will allow you even better performance than having these hardware units. So these two are different. People often confuse emulation, the Ozaki scheme, versus the low precision, mixed precision. So these are separate algorithms. So I'll describe both succinctly. So mixed precision has been done for many years, but it's been most advocated by our old good friend Jack McGrath, who's won the Turing Award, and of course, author of top 500, one of the authors of the top 500 list. So the mixed precision, I won't go into real details. If you pick details, you can read their papers. But to use lower precision to compute, but do various corrections so that you get the same result as if you were computing at high precision. And this is mostly for solvers, like linear solvers, like like for example, LIMPAC itself is a solver. So the nature of the solver, it can you can do various tricks to do the corrections based on the fact that you do have a solver result, will allow you to correct the solutions to the extent that they will you get the same answer as if you were computing at high precision. And again, I won't go into details, but it's a very simple, fairly simple mathematical techniques, it's like the Newton's method. What you can do, what you can do is, if you look here, this LU decomposition, this is the LU decomposition, and the LU can be done in low precision. And this has the highest complexity n cubic. But being in low precision, you can use the matrix engines or the tensor cores, the so-called tensor engines or tensor cores, to really speed things up. And then the correction right here can be done. It has to be done FP64, but these have much lower complexity, like linear or n squared. So for large matrices, or mid-sized to large matrices, this thing gets really speed up. And then these are expensive, but because they're linear or square, not cubic, overall you get significant speed up. And again, you get the same solution as if you were computing in high precision. Now, how effective is this? Well, this is the latest top 500 list. And then on the left-hand side, you see the list here up to number 10. On the left-hand side, you see the so-called RMAX. So this is the exaflops in terms of computing the ALU decomposition straightforwardly using FP64. So, for example, the top machine is El Capitan at Livermore, and it's got 1.7 exaflop. But if they compute using what's called HPL-MxP, now granted, the algorithm is slightly different, so I won't go into details, but slightly different, but you can by and large compare. So this is using almost the same algorithm, but using mixed precision. You compute the LU decomposition, and this machine gets 16.7 exaflops, so you get a speed up of 9. If you go down the list, you can see that for most machines, you can get almost a factor of 10, except for Fugaku, by the way, because there's the difference between low precision, high precision. Fugaku is not as dramatic because Fugaku doesn't have a tensor engine, but it still get factor of 4. Okay, so you get almost 10 times speed up. Now you also see some even bigger speed up here. These are the two Japanese machines, ABCI3, and also Tsubame 4. The successor, these two are the successors to the previous machines, GPU machines that's built at both institutions. You see that these have almost 16 times the speed up. So you wonder, why are these even superior, more than a factor of 10? Well, that's because they're using even lower precision, not FP16 or BFloat, but using FP8, which is quite amazing. When you think about it, you use some FP8, just 8 bits, well, depending on what 8-bit format, but for example, using only 5-bit, either 4-bit mantissa, 3-bit exponent, 1-bit sine, vice versa. So it's only 4 or 5 bits of mantissa precision, and only 2 or 3 bits of exponent. You still get the same results. Okay? The original the original, of course, the input is 64 bits, but compute is done in FP8. And you get 16 times speed. Can this be done in FP4, FP6 or FP4? Theoretically, yes. We haven't tested it. But again, with the significant speed up of these units, we can anticipate that you get tremendous speed up. So linear algebra solvers like LU, QR, etc. These tensor cores work significantly well to go beyond the traditional speed up as afforded by the hardware. So what about other schemes? These are solvers, but what if you don't have a solver? You just have a matrix multiply. Zero science goes. So you don't have a solver, you just have your matrix multiply become fast. So now now you resort to emulation, meaning you are computing high precision numbers using low precision arithmetic and emulating as if you are computing in high precision. But since this is a solver, you can't correct it. So you have to use the emulation very succinctly so that you get the same precision without resorting to these error correction. And there's been lots of work historically, but recently Professor Ozaki, along with our team at R-CCS, led by Toshiyuki Nomura, have come up with a series of methods called Ozaki scheme that actually allows you to emulate matrix multiply using either integer units or now some low precision floating point units. And again, I won't go into details. If you're interested, use your paper, just Google Ozaki scheme. And it's a fairly straightforward scheme that you divide up the matrix into components, to different precision components, and then you multiply all of them and accumulate. And of course, there are lots of smarts there to make sure that you do the proper correction and so forth. So what's the effect of this? So this is the result on the Grace Hopper. So on Grace Hopper, which still does have the matrix engine, FP64 matrix engine, the hardware on Grace Hopper is on 2 GPUs. If you do the real measurement, is about 90 teraflops. Okay, so again, Grace Hopper, the hoppers do have the matrix units. The peak flops for each GPU is 60 teraflops. So combined, each peak is 120 teraflops, about 120 teraflops. Of course, with the overhead, you achieve about 90 teraflops. Okay, but using a Ozaki seed, because Grace Hopper, you get almost 2 exaflops of integer compute. So even if you use emulation, the 2 GPUs, you get 250 teraflops. So now, so by use of the AI hardware, you get superior performance compared to using the native hardware. So in Grace Blackwell, the difference is even more pronounced because they got rid of NVIDIA got rid of the FP64 matrix units, but significantly enhanced the integer and floating point low precision arithmetic. So we can expect that moving forward, for example, in chips like Rubin Ultra, 300 Ultra, this is some of the estimation I've been doing. We can expect that each of the package, the Rubin Ultra package, which does contain 4 GPU dice, will get almost petaflop of FP64. And now there's a new algorithm, Ozaki 2, which I won't go into, which even enhances the performance further. And so we'll get even better performance by these improved algorithms. The Ozaki 2, I think, will be published at SC25. And what's even better is that you can see that when you go to, you can arbitrarily reduce the precision numbers. So you can do full 64-bit emulation, but you can do 56-bit emulation or 48-bit emulation. You can reduce your mantissa size, and each time you reduce mantissa, you get n squared effect in terms of performance gains. So if your application doesn't require full 64-bit precision, but it may require a little bit more than 32, but somewhere in between. Let's say you have you only require FP48 for your application, then you can even get twice the performance of this, because it's about the ratio n squared is about factor of 2. So you can even adjust these to get even higher performance. So our groups are trying to see in real application, like for example, some material science, what are the precisions versus the accuracy. That's how to satisfy the accuracy required by the applications, and in those cases, how much performance gains do we get, going even beyond the performance gains we attain for FP64. So that's one thing we're doing. So definitely in algebra, we have great hopes that by combining these matrix units and the algorithms such as reduced mixed precision or the emulation schemes like Ozaki, and then on the application side, you would control the precision depending on the applications. You get significant speed up, going well beyond. So what about memory bound codes? Okay, so one of the research that's been done by our team says if you just do straightforward porting of your codes, then you're obviously bound by the memory bandwidth. Can some of the features in GPUs can they do better? Well, not that much. So we've done some real analysis, and because of the various limitations, even if you use tensor cores and so forth, you may only get about 30% speed up at most. Okay, when you don't change your code, really fundamentally change your code. So that doesn't sound too good. But can you do better? Well, so that's what we're looking into. So this team led by Ichimura, and so they're the earthquake team at University of Tokyo, also are visiting as researchers. So what they're doing is to, so they really have to change the code. So in cases where the range of the matrix coefficients can be fairly small, so they're running earthquake code, and they found that you can go down to the matrix coefficient can go as low as 8 bits instead of full FP64, and for problems like wave propagation. So and of course you have to do some tricks to make sure you have precision. But going from FP64 to 8 bits obviously gives you 8x speed up in bandwidth. And in fact, you can get more. I don't want to go into details. So they did various experiments, and by going to 8 bits and also some other numerical tricks they play, it says here that they got 17 times speed up on wave propagation code. Of course, this doesn't apply to all structure codes or things that, for example, if the structure changes drastically, then you probably need more precision. But in certain cases, you can get significant speed up by these numerical, even the sparse problems, these numerical methods, improvements in numerical methods. Can there be other tricks? Well, this is Toru Iwashita at Kyoto University, and their team has been working on preconditioners to try to attain speed up. So the idea is, instead of applying preconditioners to reduce the iteration counts, what they're trying to do is using preconditioners to reduce the range of of the coefficients as much as possible. So then they can have much smaller bits in terms of number of smaller bit number of representations. So they can go from IPv4 to IP32 and even integers if you have the right by having a proper preconditioner. So again, that's very similar to what the HMI has done, but this time they're trying to apply it to other problems. So the sparse problems are also could be amenable to these types of speedups, and also creating tools. I think this again another publication at SC. We have a tool called Raptor that will allow you to change your code and experiment dynamically with it non-intrusively. Right? And these types of changes may be hard, but probably amenable to AI vibe coding. So we're working also. Another work is try to use AI to make those changes and not burden the program.
Satoshi, I just want to make sure we have a time check here. We've got a few minutes left before we go to Q&A, and I realize I'm looking at your slides. I realize you have a lot more to go. So maybe
but I'll just finish by saying strong scaling, weak scaling, and the rest of the slides people can look at on their own. So another thing is strong scaling. Now we have machines with scale-up networks and along with the scale-out networks like NVIDIA NVL72. So you might think that compute-bound apps or dense linear algebra has high correlational impact. So compute-bound, that's memory nor network-bound. Memory-bound apps are sparse linear algebra, so it becomes both memory and network-bound. But this is totally untrue. Okay? In fact, compute-bound apps are strong scaling. Okay, and I won't go into all the text here. If people are interested, you can pause. Please pause and read. But basically, molecular dynamics, etc., are dense linear algebra, and they are compute-bound and also strong scaling. So, and this is where scale-up networks actually work. In fact, we have there's a work by Eric Lindahl, who's his team is doing GROVAX. By the use of NVL72, MV is machine with a massive NVLink scale-up network. They get factor 2 speed up by going from normal GPU clusters to this highly interconnected clusters. So scale-up network may be the key to the strong scaling, and also some codes such as FFT-based codes like spectral methods, where we may have resurrections of these, algorithms that we threw away because we want to weak scale machines. Whereas the bandwidth-bound applications are usually have been converted into very nicely weak scaling codes. So they are amenable mostly to the use of scale-out networks only. Okay, so structured code, etc. I mean, there are some exceptions. So, but most of these modern codes scale very well to a very large number of CPUs, GPUs, TPUs, etc. So the whole deal is when you have a scale-up network. What we're currently debating, and this is not conclusive yet, because scale-up networks are not only expensive cost-wise, but also they're less stable. That limits your packaging. There are all these negatives associated with scale-up networks too. So we're evaluating what's the worth of scale-up networks, especially for these dense linear algebra codes, which again, as I said earlier, will be accelerated by these tensors. Okay? And we're doing various things. And finally, but I'd like to point out one thing before I finish. So we have all these new breed of GPUs coming about. This is what some analysis they have estimated. So in a nutshell, we're getting very good speed up on these low precision linear algebra. which is really good because full density linear algebra is good, and even for HPC it's good. Okay? Scale up network, it's getting better. They'll have higher bandwidth for again full density linear algebra or this strong scaling codes. That's good. But for weak scaling, right, or the memory bound codes, the memory bandwidth, although memory bandwidth is increasing, the caveat is that the PTDP has also dramatically risen. For example, Fugaku, when you run a memory bound code, it's about 50 gigabytes per second per watt. When you do the math here, these machines, although 10 years, almost 7 to 8 years later, almost 10 years later, has only increased the watt per bandwidth performance only by a factor of 2. So this means that for the majority of this memory bound codes, which constitute about 70% of the codes we run, and also very important for inference, right? Because inference, when you have inference, especially in transformers, where you have the decode stage is basically dominant, and decode stage is all about bandwidth. Okay, so it's just like a L2 plus. So that's where we will stagnate in both HPC, also in inference, AI inference. We are stagnating. So we really need innovations in memory, and that's again exact. And by the way, that's where we are working on. I can't go into details here yet, but that's what we're working. My final slide. So, but if we resolve these problems, also resort to some techniques like surrogates, which obviously I didn't cover, but become very popular. We hopefully will get excess of more than 2 orders of magnitude speed up in some cases. And for AI, of course, we will get something like zettascale machines. Will be more predominant for very large-scale supercomputers, including Fugaku Next and low precision. So hopefully in the 2030, we will have convergence of AI and HPC by the use of very advanced algorithms and also the right architectural designs. But the biggest problem here is memory. So that's where I think we really need to focus on. And that's where the next innovation will come in terms of this conversion. Okay, so that's it. And thank you for listening.
Great. Thank you very much, Satoshi. We're at 10 minutes to the hour, so I'm going to pick one question out of the Q&A. This is from Michael Hero. And Satoshi, he asked, can you discuss the practical risk of using low precision when the condition number of the matrix is large, rendering low precision calculation unusable, even with iterative refinement?
Yeah. Yes, that's for, yes. And firstly, there are many aspects to the answer. The first is how much of these matrices appear in practice. Okay, so we're doing various studies to see for real problems, for real practical problems, how much these show up. So far, so this seems to be good. But in terms of solvers, in terms of matrix multiply, like Ozaki seen, it's much less than a concern. For solvers, yes, it could be a concern. But again, that's something we are trying to look into to see whether there are some disruptions there. That said, for things like Ozaki scheme, there are rudimentary checking algorithms where you can scan the in some cases you can predetermine whether some of these precision there will be some violations of precisions because of the extreme because condition numbers or some of the other values would exceed the limits that's dictated by the algorithm. So the trick will be to have these checks built in, and if these checks are low enough in terms of overhead, they'll be practical. And for real libraries, for example, some vendors are building, for example, Ozaki, for matrix multiplying, Ozaki scheme, vendors are coming up with these lightweight checks, and they're incorporating into this to the libraries. So then what happens is, if it passes, it's a lower overhead, maybe a few percent to 10%. If it passes, then you go to the accelerate path. If it doesn't, then you go the slow path, but you get the right number. So that will generally be the strategy, I think, to make sure that you are okay. And if you know that you're going to be okay because of the application characteristics, then of course they'll give you option to actually eliminate the checks if you know you're going to be safe on the application side.